In this lesson, we're going to take a look at normal distributions. And these are a little bit abstract right now, but that's okay because over the next 15, 20 minutes or so, hopefully you'll become much more comfortable with them to the point where you can use them effortlessly. Once you get them, they're actually not that tricky to use. Just trying to understand exactly what they are is a little hard, which is why we're going to start off with a little bit of a slideshow, just to kind of go through some of the properties and the general idea of what a normal distribution is. First of all, I'll point out that most people have not necessarily heard of a normal distribution, but they have heard the term bell curve before. And the idea of a bell curve is that when you've got a set of data, oftentimes it is normally distributed, which is a fancy way of saying that most of the values are central to the data set. So a lot of things will be towards the middle. And then as you move away from the middle towards the extremes, the number or frequency of data points will drop off fairly dramatically. So if you think about marks in a class, normally you've got an average, a class average or a class median somewhere in the 70s, and then it becomes, well, there's lots of people with marks that are similar to that, and then it becomes less and less as you go up towards 100 and less as you go down towards the 50s or lower. So what we're going to talk about is kind of an ideal normal distribution. And of course, in real life, nothing will end up being ideal, but you'd be surprised on how often a data set, even if it's a little wonky, is actually a really we could use normal distributions to really closely approximate what's happening in them, even if they're not perfectly normally distributed. So one of the key features of a normal distribution is that it is symmetric. It does have approximately equal data on each side. So 50% of the data points will be below the mean median mode and 50% will be above. And the mean median modes themselves will all be similar values. Again, in an ideal world, they'd all be exactly the same. Now, if I look at this bar here, this bar graph, now I realize that this is actually a horrible mismatch of bar graph and histogram. It's a bar graph in the sense that it is labeled in the middle and treating the values as if they are discrete. It's histogram-like because the bars are touching and the data is actually supposed to be, well, actually is, heights are going to be continuous. So don't get too caught up on the details of this. What I do want you to notice is that if you took all of the bars and you added up their frequencies, the total frequency, which ends up being the total area of all the bars together, will represent 100% of the data points. And if I just flip back to the curve here, the idea for this curve is that it's representing an approximate shape of those bars. And if you picture it in your head, an infinite number of bars. In fact, if you look at this one really closely, you'll notice that the curves are pixelated. So they could be thought of as a bunch of bars side by side. And if you took all of those bars and put them together, the amount of data contained in them should represent 100% of the data. Okay. So why use them? And the reality is you can get a lot of information out of a data set knowing nothing more than its mean and its standard deviation. If you have those two things and you know that the data set is approximately normally distributed, you can make all kinds of conclusions about what that looks like. So if in this picture here, we actually have a bar graph again, which is a little bit of a poorly done one. I'm pulling these off because they have decent pictures that are going to help us understand this idea, not because they're perfectly done. Um, this one has a bar graph representing continuous data, which is already a no-no. It is, however, like a bar graph separating the bars apart. But what it's getting at is that the bars are representing a certain shape, and the yellow curve underneath is an approximation of that shape, and that is the normal distribution itself. So if we have nothing but the mean and the standard deviation, we can make several conclusions about what's going on. The first thing is that in a normally distributed data set, almost all data will fall within 3 standard deviations of the mean, whether that's up to 3 above or down to 3 below. Almost 100% of data will fall within that range. If you're beyond +3 or -3 standard deviations, you're that rare 1 in 1,000 or lower data point. Now, the nice thing is we can take all data sets. So on the left, we have a normal distribution representing something. I don't even know what it's measuring, but apparently something with a mean of 1010 and a standard deviation of what looks like 20. It's going up by 20 three times on the bottom and down by 23 times as well. But we can replace those numbers with just a standard normal distribution, which is the graph that we're going to kind of use and try to memorize or try to understand. And it's just going to say that the mean is 0 standard deviations from the mean, and then the +1, +2, +3, -1, -2, -3 are up to 3 standard deviations above or below that mean. What we're actually going to do is, instead of taking a standard or normal distribution and make it standardized, we're going to use the standardized distribution table, our distribution graph, and then we're going to try and put our specific situation on top of it. So we're going to take the mean and the standard deviation and fill in the numbers that we need to solve problems. Now, here's a graph showing several different bell curves or several different normal distributions. The only real difference between them, I mean, they all look like they're different shapes, but they're actually the same shape. It's just whether or not it's condensed or stretched out. All that's different between these is basically what is the mean and how much is the standard deviation. So the three graphs or three colors down the middle, the blue, the red, and the yellow, all represent normal distribution with a mean of 0. And again, it's kind of completely arbitrary. This is just showing you a general idea. Don't worry about the variables in the notation. But what it is also showing you is that the blue one has a very tight or very small standard deviation, meaning the data is very close to each other and drops off extremely quickly as you move away from the mean. Whereas the yellow one has the same median or same mean, but it drops off much slower. It's much more spread out. The green one is just showing that you can slide that mean anywhere you want, up or down, to whatever value you want. So these all look different, but they're really the same thing. Okay, now for some notation. You're going to see this fairly frequently. It's a nice short way of writing out a longer idea. And the way that we would read this, if I was trying to actually read what it says in symbols, is X squiggle, and no, that's not the official term, but we're going to call it a squiggle, X squiggle N bracket X bar comma sigma squared. Now what that really means, and this is something people have a little bit of struggling with, and it's not hard, it's just you actually have to memorize it, is that that is not an X is approximately equal to N. Also, I should point out that the X can be any letter you want. It's going to be the data set in question. So it could be X's, which is usually a generic data set. If we were doing a distribution of a whole bunch of, for instance, weights, we could have W squiggle, or we could do heights and do H squiggle, or whatever we want. That's an arbitrary variable. The squiggle is short form for well, sorry, I should say the squiggle N has a short form of, has a normal distribution. So that is not a variable. That's actually a letter that we use to define normal distributions. So this says X is approximately normally distributed, or is normally distributed to the point where we're okay with it. And then the two numbers inside the bracket are going to represent the mean and, unfortunately, the variance. You remember when we talked about standard deviation, I really quickly mentioned that the variance would be used in one place, and this is it. It's this notation. The good news is we're going to kind of bypass variance and just say the square root of whatever number's in there, since variance is standard deviation squared. The square root of that number is the standard deviation. So often you'll see it written like the example there, x squiggle n 6 comma 1.5 squared. Well, by writing it as 1.5 squared, we can really easily see that the variance is 1.5 squared, but the standard deviation is 1.5. If it wasn't written in that form, if it was actually written out as 2.25, we would take the square root to get the standard deviation, and the square root of 2.25 would be 1.5. So x squiggle n, comma, or bracket 6 comma 1.5 squared, we would read that as x is normally distributed with a mean of 6 and a standard deviation of 1.5. Or you could say a variance of 1.5 squared or a variance of 2.25, but we'll stick with standard deviation. Now, this empirical rule, this is going to be hugely important for us for solving problems. And it's going to be a fairly big step in understanding how normal distributions work and what standard deviation really kind of means. So it turns out that if you have a set that is normally distributed with a mean of x bar and a standard deviation of sigma, regardless of what those values are, approximately 2/3, or more specifically 68% of your data will fall within one standard deviation of the mean. So it'll be within the mean plus one standard deviation and the mean minus one standard deviation. So for instance, if we said we had a class with an average of 70 and a standard deviation of 5, what it means is 2/3 of the students would have a mark between 65 and 75. That's one standard deviation above or below the mean. 95% of students will have a mark plus or minus 2 standard deviations from the mean, so between a 60 and an 80. And 99.8% of students would have a mark between 55 and 85. Okay, so this example is probably not great since we probably do have students with above those marks or below those marks, but the idea is the same. If we know the mean and the standard deviation, we know that 68% of data will be within one standard deviation of the mean, 95 will be within two, and 99.8 will be within three. And I think if you have basic math skills, you can acknowledge that 99.8% is within three standard deviations, meaning that 0.2% is beyond it. And that would be 0.1% above and 0.1% below. So this is basically saying that if you have a normally distributed set, only about 1 in 1,000 data points will fall more than three standard deviations above the mean, and only about 1 in 1,000 will be below three standard deviations below the mean. So if you were thinking about the height of students at your school, and your school has around 1,000 students, there's only one student in the school who should have a height that's more than three standard deviations above the mean, and only one that's shorter than three standard deviations below the mean. And 2/3 of students should be within one standard deviation of the mean. Now, I will point out that these numbers 68, 95, and 99.8 are slightly approximated. They're rounded off a little bit to make the method easier. And when we get to our next lesson, we'll see how to get a more precise value. But for now, those are the three numbers that I'd like you to kind of memorize and recognize: 68%, 95%, and 99.8%. It's often called well, it is called the empirical rule, but it's often just referred to by those three numbers: 68, 95, 99.8. Now, I've broken them down here on this graph, and the truth is you don't need me to give this to you. You can calculate this and figure it out on your own. If you know that the middle two bars together are 68, then obviously each of them, because of symmetry, is 34. Likewise, between plus and minus 2 standard deviations, you know you've got 95% of the data. You've already accounted for 68% of it. That means that you've got 27% left. Half of that 27 goes on the left, half on the right. That's the 13.5s. To go from 95 to 98, that's another, 99.8, that's another 4.8%, so 2.4 on the left, 2.4 on the right, and then the remaining 0.1% on the left and 0.1% on the right. And drawing this graph and putting these numbers in is actually fairly helpful for solving problems. Okay. Now, here's an example of what was, and I don't know what it was from, but it was a a distribution of actual data, and you can see that it doesn't perfectly follow the normal distribution. It's not perfectly symmetric. Some of the bars are a little too high, some of the bars are a little too low, and it's amazing how little that seems to matter when it comes to actually doing an analysis. So my class has tried this in the past where they go collect data and we try to see how close it is to a normal distribution, and the normal distribution approximation stuff comes ridiculously good, so that we can actually treat this like it's a perfect normal distribution, and the math works out almost precisely. We still get approximately 68% of data points within one standard deviation, and so on. It's fantastic. Okay, so let's go over to the actual handout for the lesson, the actual like filling in blanks and doing calculation stuff. And I'm going to skip over it fairly quickly because most of what's at the beginning part of the note is actually just kind of a rehashing of what this little mini presentation was. Okay, so here we are on our note. And again, most of this, if you start to read through it, you'll realize it's just a summary of the kinds of things that we were saying on our PowerPoint. So I'm going to skip down past the notation, which we covered already, and get to an actual slight example. So what is the mean and standard deviation of x squiggle n bracket 9 comma 4? Well, first of all, let's just remind ourselves what that means. It means that x is normally distributed. The squiggle n is not approximal equal to anything. It's just short form for is normally distributed. And the first number in our bracket is the x bar, or the mean. And the second number in our bracket is the variance, which is actually standard deviation squared. You don't have to write that down. You could immediately jump to the standard deviation is 2. For those of you who are keen at math and might pick up the fact that sigma squared equals 4 means that sigma could be plus or minus 2, just be aware that, kind of like the Pythagorean theorem where you're doing side lengths and they're always positive, standard deviation is always, always, always positive. And if you go back to the equation we looked at in the last lesson, I think you'll see why. It's the square root of a bunch of stuff squared. Has to be positive. Okay, so this, I just want to go over this graph again, just to make sure that you're good with it. Again, reminding you that 68% of data falls within one standard deviation of the mean. To be technical, it's 68.2, but don't worry about it. 95% of data falls within 2 standard deviations of the mean, real numbers 94.8, and 99.8% of data falls within 3 standard deviations of the mean, and that number is slightly approximated as well. So if we go with that, then it's 1 in 1,000 that falls beyond plus or minus 3 standard deviations. One out of 1,000 on the top numbers, 1 out of 1,000 on the low. I thought I'd put these in here because you can keep going up to higher standard deviations. It just means that values are more and more rare. So I think this part is actually kind of interesting. The true number for 3 standard deviations isn't 1 out of 1,000, it's 1 out of 741. So if you think about your school population, about 1,000, again, you'd have about the tallest person would be the one person above 3 standard deviations, and the shortest person would be 3 standard deviations below, or a little more than 3 standard deviations. By the time you're getting to 4 standard deviations from the mean, you're talking about 1 in 31,000. So let's say we were talking about intelligence. If you were 4 standard deviations above the mean intelligence, it means you're approximately, in a city the size of Kitchener, about the top 10 people in Kitchener for intelligence. If you were 5 standard deviations above the mean, it means you'd be approximately one of the top 10 smartest people in Canada. And if we do it for any other measure, you'd be the top, one of the top 10 tallest, or one of the top 10 heaviest, or one of the top 10 whatever. 5 standard deviations being 1 in 3.5 million. And by the time you're 6 standard deviations from the mean, you're talking about 1 in a, let's see, that's thousands, millions, billions. Okay, so 1 in a billion would be 6 standard deviations from the mean. So currently on our planet, if you were 6 standard deviations above the mean intelligence-wise, you would be in the top approximately 7 or 8 people on the planet for intelligence. And likewise, if you were 6 standard deviations below the mean for intelligence, you'd be one of the dumbest 7 or 8 people on the planet. Hopefully no one in the class is in that category. Okay, so let's actually try solving a problem using this simple table with no information other than the mean and the standard deviation. So for our example 2, we have a pop machine. By the way, this was inspired by my teenage work at McDonald's. It's not exactly accurate, but it's kind of close to what actually did happen there. Pop machine at the restaurant dispenses a mean of 650 milliliters of pop into a glass that can hold 680 milliliters. The pop machine has a standard deviation of 12 milliliters. That means that 2/3 of the time it will give 250 milliliters plus or minus 12 milliliters of pop, and so on. So we want to find out what percentage of glasses will overflow, and if the minimum size that can be served is 640, what percentage of drinks should be topped up. So here's what we're going to do. We're going to take our standardized normal distribution graph there, which just has the mean plus and minus 1, 2, 3 standard deviations, and the percentages on it. And this is the beauty, is that's a universally true standard deviate, or sorry, universally true normal distribution graph. Now we're going to apply onto it our situation, which for the pop dispenser is going to be 650 milliliters for the mean, and then every standard deviation is going to add or subtract 12. So I'm going to stagger these numbers just a little wee bit so that it's a little easier to see. But if I go up by 12s, that's going to take me to 662, 674, and 686. And by the time we're 3 standard deviations above the mean, only 1 in 1,000 cups is going to have more than 686 milliliters of pop in it. And similarly, going down, we'll subtract off 12s. That'll give us 638, 626, and 614, if my math is correct, and hopefully it is. Okay, so now what I'm going to do is I'm just going to change colors for a second. Let's go to red. I'll use red for overflowing because we don't want that to happen. Red is usually make sure that doesn't happen. And it will overflow if it goes over 680 milliliters of pop. Well, where is 680 on this graph? 2 standard deviations is 674. 3 standard deviations is 686. So it's actually going to be right in the middle. And what I'm going to do is look at the area under the curve there. So that's going to represent this part up here. And we'll do the math in just a moment, but before we do that, I'm going to actually switch colors and do the same thing for the ones that need to be topped up. They have to be topped up if they're under 640. And 640 is going to be about here, give or take. And I'm just going to try not to overpower the numbers that are there, but that's going to be that region. So those are the ones that need to be topped up. So now to look a little bit at the math behind them. For part A, the red part, I'm going to try and actually just do a slightly bigger graph here, or slightly bigger version of this. I do want to point out that this part here, it actually looks like that between 2 and 3 standard deviations. Because the part to the right of that, the 0.1, we know that's 0.1. We know this is 0.1%. And we know that this entire thing is 2.4%, but we only have half of it. Now I'm going to be careful here, because when I say we have half of it, we have half width of the shape, but not half area. So a lot of people want to say, well, it's halfway from the left to the right, so it's 1.2. But if you look at that, and I said that was a piece of, I don't know, a very weird shaped piece of pizza, and I cut it in half, and you got the right side and I got the left side, you can clearly see I'd be getting a lot more. So this part here we don't want, and this part here we do. And the best we can do at this point is approximate that. So if I look at that as an actual area, I'm going to note that it's definitely less than half. I don't know how much less than half, but a little less than half. So I'm going to guess that it's maybe 1% out of the 2.4. So maybe the right part is 1%, the left part's 1.4, maybe even a little less. And you know what? I think I'm actually going to just approximate this as 0.9%, so that when I put those together, I can say the area is approximately 1%. And I'm going to put approximately there, although to be honest, anytime you're using this method, it's going to be approximate anyway. All right, for this other piece, the yellow piece, the good news is this part's definitely full. This part's definitely full. The 13.5 is definitely full. The only part that isn't is that little sliver between -1 standard deviation and the mean. Okay, same idea here. That represents a width of 2. because it was 640. So it represents a width 2 out of 12. That would be 1/6 of the width. So 1/6 of the width, if that was 1/6 of the area, it would be 1/6 of 36, which is just under 6%. However, that's also the shortest sixth. So the sixth of the width, but it's not a sixth of the area. So I don't know what it actually is, but I know it's going to be less than 6%, just because if it was, for instance, zero point 0.2 over here, it would definitely be much larger. So I'm going to guess that as, I don't know, 5%? Yeah, it sounds about right. 5%. It might be 4%. I don't know. Um, but you know what? If we're within 1 or 2% of the correct answer here, I think we're doing okay. And by the way, we are going to see a method later and we can calculate it exactly and we can compare how far off we were. So if I add together the pieces I have the 0.1%, the 2.4, the 13.5, and then about 5 more. And I think the total on that is going to be about 21% would be my guess. And you know what? Maybe it's not 21%. Maybe it's actually 20%. Maybe it's 18 or 24. I don't know. I just know that it's in the ballpark of 21%. So basically what I'm saying is if you're an employee at the restaurant, without getting into extreme details in that number, about 1 in every 5 cups of pop is going to have to be filled up, and only about 1 out of every 100 is going to overflow. And you know what? If you're the employee and it's 1 out of every 90 that overflows or 1 out of every 110, I don't think you care. It's about 1 in 100. And likewise, if I say 1 out of every 5 needs to be filled up, if it was really 1 out of every 4 or 1 out of every 6, I think you'd probably be fine with that too. Just a ballpark number. So that's how we can use this graph and this basic rule to solve some problems. Let's try one more of these just because a little practice never hurts. So we have an apple tree in an orchard is found to have apples with masses that are normally distributed with a mass of 112 grams and a standard deviation of 9 grams. So let's put that into our notation that we learned. And again, our notation always start off with X squiggle, but X is arbitrary. So for this case, what is normally distributed is the weight of apples. So we should use a variable that's a little bit more descriptive. We could use W for weight. I'm going to choose A for apples. The apple weights are normally distributed. And then I know that the mean is 112. And the standard deviation is 9. So remember that it's actually the variance that goes here, the standard deviation squared. I could write in 81, but I'm just going to plug in 9 squared. And by the way, the only reason it's variance is because the person who made this up decided that that was how that was going to be done. If it was made nowadays, I don't see why anyone would use variance when they could use standard deviation. It's a much more meaningful, much more useful tool. Okay, and now given that, we want to find out the percentage of apples that have mass smaller than 100 grams, larger than 135, or between 110 and 120. So I'm going to change colors again and draw those areas on my graph. So the smaller than 100, actually, before I do that, we should put numbers on our graph, which would make it a lot easier to actually use. Okay, so again, the mean is 112, and each standard deviation is 9. So that takes us up to 121, 130, 139. And it takes us down to 103, 94, and 85. Now I'm going to use the red to represent the ones that are under 100 grams. 100 grams is actually going to be about here. Ooh, I don't want crayon. I want that. But first I'm going to erase what I made a mess there. So 100 grams is about 2/3 of the way through the bar, so it's about here. And again, I'm going to shade this in, but I'm going to try not to go over any of the numbers that are there. And then I'll use yellow for the ones that are over 135, which is about here. A very small sliver. And I'll use green for the good apples that are between the 110 and 120. So 110 is about there. And 120 is just shy of the next line. That's super messy. 120. Oh, and I didn't actually label the other one while I'm at it. That was the 135. Okay, so now we're going to go back and see if we can actually do those. The ones under 100, it's going to be the 0.1% plus the 2.4% plus some part of 13.5. Yeah, it's like 2/3 of the width, but they're the short 2/3. If it was an even if it was exactly 2/3 of 13.5, that would be what, about 9. So I'm going to guess that maybe it's more like 7.5 or 8. And I'm just going to guess 7.5. It actually makes the number a little bit nicer. So 7.5, 8.5, that gives us a 9%. So roughly 9% of apples are going to fall into the category of under 100 grams. The over 100 grams is the end 0.1%. And again, it's pretty close to the one that we did in the last one. In this case, it's a little wee bit less than half the width, and it's the smallest half. So I'm going to guess maybe it's more like 0.5. I don't know. Again, really super approximate. Uh, or if you put down 0.7 or 0.8 or whatever, that's totally reasonable. Either way, I'm going to estimate that it's probably around 0.6%. I don't know what it is. I just know it's small. So I'm going to guess this is about 0.6%. And then finally, the green part in the middle. Now this one's a little bit trickier. Here's how I'm going to look at it. So if it was the entire area between the mean and one standard deviation above, it would be 34%. I'm removing this small sliver, but I'm adding in this bigger sliver. Not only is it twice as wide, but it's also taller. So I don't know. I'm going to guess it's a little higher than 34% when you put those together. I'm going to guess maybe 37%. But again, it's a little bit of an approximation there. And depending on how you look at it, you might get a slightly different number. But I'm going to guess 37%. And that's about as good as we can do with this method. The good news is our next lesson or two will be looking at least our next lesson, we'll be looking at how to find these numbers more precisely. And I'm going to actually make note of these answers that we got here in our approximations, and we can compare them and see how good they were later. All right, I'm going to leave things there, and we'll meet you in the next lesson on z-scores, which is a mathematical official way of dealing with normal distributions. Until next time.